Thank you. Okay. All right. So I want to thank the organizer for giving me an excuse to come to France on public fundings. Right. What? So the title is has some funny words, and I guess I should explain something. But anyway, this is all joint. This is mostly joint work with. By the way, can you hear me in the back? I'm not very used to talking, speaking this in a room of this size. So, come on. Well, I haven't been teaching calculus in the United States for long enough. So, anyway, so this is mostly joint work with Hsian-Hua of St. Louis, and there's some paper about it. I think it seemed to be customary to tell everybody what the archive numbers are. So that is. I'm sorry that this is from last year because I really don't have anything new to say this year. Okay, so the plan is roughly this. I'm going to talk about Gromov-Witten theory of Gerb, which is some sort of, deviates from the mainstream Gromov-Witten theory that you've been hearing over the past 3 weeks. For that, I want to apologize, but I don't feel like to. But, and as you will see, there are some interesting features that happens in this consideration that you don't really see in the global mirror symmetry business or whatever. But there are some interesting features here. So the plan is to discuss what gerbs are and what there's something that I like to call gerb duality. And I want to explain what that means. And then we go to Gromov-Witten theory of. There's some Gromov-Witten theoretic aspect of this gerb duality. And that's going to be that's the reason why I'm here, right? Because I'm supposed to talk about some Gromov-Witten theory. Okay, so I didn't bother to look in the dictionary, but I'm pretty sure the word gerb means something in French. But for me, gerb means something entirely different, I suppose. Okay, so let's just fix for the rest of the talk some finite group called G. And BG is the classifying stack for the group G. Okay, there is a tendency for this thing to fall, apparently. I don't seem to have a good solution for it. Everybody is unique in his or her own way, right? Okay, so B is just going to be some base. I just call it base space because this I can be flexible in what I mean by space. For example, it can mean sometimes it can mean symplectic orbifold, sometimes it means projective algebraic variety, sometimes it means smooth steady multiple stack, whatever. So I just put space here. So G-gerb is just something that is a map that goes from something I call Y to B, which is quote unquote a principal BG bundle. I put it is in quote because it's you can if there's anybody who's really care about stack in the audience, they're gonna complain. But what I really mean here, this is a good way. This description is a good way to think about what this should be. Is you want something that looks locally like a product of BG with something, then you worry about how to glue those things together to form something global. So so let's just describe how that works. So pick an open cover. Yeah, now I'm in trouble. So pick some open cover. I hope you guys have enough chalk because I've been known to break chalks very easily. We'll see. All right. So you pick some open cover such that if you look at this map and restrict it to any of the any of this open cover, this becomes a product. Okay. And then you start worrying about how once your open covers overlap, what happens. And the standard way to build principal bundles tells you that you have to specify some way to glue fibers. So therefore you try to do it. So on double overlap, you're supposed to be able to glue BGs, or in other words, you need a map from BG to yourself, which is the same thing as saying you give yourself a choice of automorphism of G. Now, if you're looking at a triple overlap, the usual theory of fiber bundles will tell you that there's some compatibility condition between the gluing data. So that would look like something like this. And now this is the place to start really complaining about the fact that I'm gluing stacks, because the objects involved in these maps are stacks, there is a tendency of demanding diagrams to be two commutative rather than just one. And if you just demand this equality, it will be one commutative, which is, by common wisdom nowadays, the wrong thing to do. So you have to allow yourself a flexibility of natural transformation to be put in here. That if you translate the terminology correctly, it means that on the triple overlap you need to prescribe some group element, say Gij in the group, such that this equality holds true up to conjugation by that element. Okay, and of course there's some further compatibility condition among these group elements and these gluing map on quadruple overlap. And I'm just going to write it down you. Okay, so that's it. That's all you need to be able to glue all these products of BGs into a global object defined over B. So in short, this G gerb is just some map from Y to B, which locally looks like a product. And because you're working in the category of stacks, you have to be careful a little bit about how to glue them. And the gluing data is given here with this constraint. Okay.
So you mean real open cover or you mean étale cover?
That goes in. That also has to do with the flexibility I'm allowed here, because if I'm working with implied orbitals, I do mean like genuine Euclidean neighborhood, Euclidean open. But if I work with the Imam stack, étale open. But so At this, I mean, this is in some sense a concrete enough description, but it's still better to see some real examples of gerbs so that you're convinced that this is not something I just made up. So some examples. First of all, nobody stops you from just taking the product with BG by itself. It comes with a projection map to B, and that's a perfectly well-defined gadget, and this is usually called a trivial gerb for trivial reasons. Okay, and well, let's see. Let's say you have short exact sequence of finite groups, say, with G being that G that I fix. Then every time you have something like this, you get you can take the classifying stack and gives you a map from BH to BQ, and this is a G gerb. And of course, there is some classical theory that tells you how to classify those extensions. And so if there's some book that I found, I don't know exactly what, I don't remember the book, but there's some book that I found that describes this thing. And if you look at what's written there, is the classifying data for such an extension is exactly those. I mean, translate appropriately. Nothing is abelian necessarily. You don't like the fact that these are non-abelian? I mean, at this point, nothing has to be abelian, I don't think. No. Yeah. Okay, you can soup up this example a little bit. Namely, if you have some manifold, say, and if somehow H axon is such that the induced G action is trivial, then if the induced G action is trivial, then you can just pick a splitting of Q into H. Then that will allow you to define a Q action on M. And hence, you can define something like this. And this is also a G gerb. Okay, so so the first example is trivial. The second example is classical in some sense because it's basically just classifying extensions of groups. The third example is going to be more geometric. So let's see. So let's say you have some complex line bundle on your base somehow. And let's say you have some integer. And one of the sometimes in algebraic geometry, people ask whether such a line bundle has a Rth root or not. Sometimes, sometimes in curve theory, you would like to know whether your canonical bundle has a square root or not, which I believe is the subject of some talks in the first week. Okay, right. So sometimes Rth root exists, sometimes it doesn't. But there's a way to bypass this problem by simply saying, okay, let's look at the stack classifying all the Rth roots. The notation is the Rth root of L over B. This stack means that if if you look at the objects over any scheme S, this should be well, object over any S. Well, okay. Yeah, well, it doesn't really look like way, but anyway. By an object over S, I should mean that you have some map from S to your base B, and then you have some line bundle M over S, and then the isomorphism of the R power of N with the pullback of L. Right, so that's what I mean. That's one thing that people do. If you want to study some objects, you don't know exactly how to pin down a specific one. You classify them all. So it's not very hard to check that this. First of all, this has a map to B because you just forget about the data you choose. Simply remember this map, and this map is a mu algebra. It's a rather trivial one, but it came, from reasonably interesting consideration. Okay. And maybe just to sort of convince you that this thing is really there, not something artificial. I mean, if you happen to run into some ineffective orbital, meaning that every point, at generic point, you can have non-trivial stabilizers, then these things are always a germ over something effective. So, on the other hand, so first of all, this if you decide to work in serial orbitals, it's inevitable that sooner or later you're going to have to deal with this sort of thing. And secondly, what? Secondly, this germ thing is purely orbital theoretic because you really want the generic point to have something non-trivial attached to it, and you don't see that in the theory of schemes, for example. So this is really yes.
Can this argument also be described as the quotient of, you take out the zero section, so you get some C star bundle, then you quotient by C star.
Yeah, sure. Yeah, there are different ways to present it, but this is sort of this motivates better the fact that this thing is geometric. I want some example that's geometric, that's not too artificial looking. Okay. So in any case, this is something that's there, and the fact that it's there doesn't mean that you have to study them. There's got to be some reason that that suggests that it's worth thinking about. Okay, there's something I need to keep. Yes. Kind of wanted. Sorry, let me keep this board. Let it go up there. Doesn't do too well when it's red. Okay. So. So now there's something that I call the germ duality, which I want to explain. But before that, let me give credits for this thing. It just happens so often that in this particular subject, people often draw inspirations from physics papers. And this is one of those instances as well. So there's some physics paper written by these four authors, and they talk about something they call decomposition conjecture, which was about gerbs, and that's what I'm going to call the duality. And of course, I'm going to explain what it means. Just to set the record straight, this guy is not a physicist. This guy is not a physicist, but nevertheless, they write physics papers. Okay, so So once again, Y mapping to B is a G-drip. Okay. So there's so out of this G-drip, I can define a principal bundle with fibers being the group of outer automorphisms. Okay. So first of all, I claim that I can, given this thing, I can define a principal bundle with fibers being outer automorphisms. And okay. Well, with that description, it's not hard to see how you want to do it. You see, look at the constraint on the gluing data on triple overlap over there. And there is, as I explained, the ambiguity that you have to include because of the fact that you're working with stacks is you have to allow the conjugation by a group element, which is by definition what we call inner automorphism. So if you decide to model out inner automorphism, and remember these phi data are automorphisms of G. So if you simply take that equation and project it down by modeling out all the inner automorphisms, you get an equation that looks exactly like what you would have if you are trying to group principal bundles in the usual way. So take that and do it, and then you get a principal bundle with fibers being outer automorphism group, and that's what this is. Okay. You can do it. Now, okay, now here comes the correct thing to do. So, I mean, I guess it's reasonable to say that representation theories are important. So every time you see something you can define representation theory on, it's worthwhile to consider what representation theory tells you. So in this case, let's look at, I'll take the group G and look at the isomorphism classes of irreducible complex representations of G and denote that by G hat. Well, okay. So at this point, it's a set of, and I can also think of it as just some disjoint union of points. One point corresponding to one isomorphism class. Okay. All right. So what am I going to do? So you can define action of the outer automorphism group on G hat from the right, given by the following construction. Say you have, in fact, say you have some representation of G, and say you have something in the outer automorphism group. Well, not quite, sorry. In the automorphism group. And this gives you a precomposition, which is, again, a map from G to the endomorphism of 0, which is, which is a representation. Maybe I should use GL instead of endomorphism, sorry. But anyway. Okay, so first of all, this construction works just for any representation, any automorphism. But then you realize that first, because well, first of all, you're taking isomorphism classes, so you don't really care about the difference between an representation or its conjugate by some fixed group element. But you see, if you have two representatives of an outer automorphism group element, you get, I mean, they differ by inner automorphism, which is conjugation, which is inner, therefore preserves isomorphism class of representations. So therefore, this construction descends to an action of auto-automorphisms on G hat. Okay. This is some, some standard subtlety about isomorphism classes. Now here comes one of the main definitions. Okay, so I'm going to define some space called Y hat, which is going to be the natural thing to do. You have that Y bar over there I explained. It's a principal Ology bundle. So it in particular has an Ology action. And you have G hat that has an Ology action on the right. So put them together, modeled by the diagonal action. And strictly speaking, you should be taking the stack quotient. Yeah, I'll do that. Okay. And it's not, of course, not clear why you want to do this, but it's not meant to be clear at this stage anyway. So you have to bear with me for a little while. I should, at this point, show you some examples. In the case when your job is BG over a point, say this BG hat is just G hat. Right, because the principal Ology bundle is trivial, and all you're doing is, and because the mixed construction, you're killing the entire fiber Ology and leaving G hat alone. What was that? Yeah, the other example is not, well, okay. Let's see. So in the case you have BH over BQ, BH hat is, so take G hat, you take G hat and quotient out by some Q action. The Q action came from the fact that you have a map on Q. You can choose any map from Q to H that splits the sequence, additively. Sorry, that splits the sequence set theoretically. And conjugation that defines for you a conjugation which becomes automorphisms of G. Anyway. So finally, in the case of root job, in the case of stack of as root, the dual is, well, yeah, you have to check a little bit, but the dual is R copies of B, disjoint union. Okay, good. Now it's good, right? Good. Okay. Now, this is not just it. There's some additional thing I have to define only in order to formulate the duality. So, so that construction came out of the following consideration. You can consider, say, you can consider a family of vector spaces. Oh, Jesus Christ. Given by the following construction over the point. What's my notation? What's my notation, really? Yes.
So in the third example, is that union of B somehow has the mu R acting on that natural way? Because if I take B to be a point, L is trivial for this case. And isn't that correspond to the case where the right hand side mu R hat?
B is a point, then
Which is odd points, right?
yeah, mu hat is just odd point.
Yeah, exactly. So what I'm asking is that union B has the natural not for a variance, just the trivial order.
I mean, yeah, I mean, but so far hasn't been used anywhere. So, any other questions? Okay. So now here's the. I mean, the next thing is going to be really weird. I promise you. So you consider the following family of vector spaces. Okay, so, well, on y hat, but you start thinking about how to associate such a thing on before you take the out G quotient. Namely, if you look at y bar cross g hat, the point in here would be x comma some class of representation, and there is a natural vector space that associate that you can attach to this point, namely. V-rho, which is the vector space corresponding to a representative of the representation in question here. Okay, so I guess I should have said in the early on that when I fix this set G hat for each isomorphism class, I fix a representative, and that's going to be the representative I work with throughout. I can do that, right? So you can obviously see that this is going to give you a family of vector spaces with jumping dimensions, of course. Well, not necessarily, but sometimes. And it's going to descend, after you take the quotient, it's going to descend to, again, a family of vector spaces. The unfortunate thing is that this fails to be a vector bundle. Okay, it's measured by, okay, the failure of this being a vector bundle is measured by something. The reason why it can fail to be a vector bundle is, of course, the Green condition. The Green, and, well, you're going to have to sit down, and, well, I guess you guys are all sitting down, but you're going to have to spend a little while just going through the definition and see that the Green condition fails. The Green condition could fail, but it may fail in the most mildest way, namely the Green condition fails up to a scalar. Namely, the equation like that is just instead of equality, it's equal up to some constant. So that means that the failure of this to be a vector bundle is measured by some U1 value Tuchel cycle. Let's call that C inverse. Tuchel cycle on y hat. Let's call that C inverse. And there's some standard map that takes U1 to itself, and namely just take any element and send it to its inverse. And this will give us, so if you take this U1 value Tuchel cycle and apply this map to it, then the result is C. Okay. So like I promised, this is going to get really weird. First of all, it's not well, I haven't actually explained the duality, so we don't know why this is supposed to be interesting. But I mean, it's reasonable to consider this family of vector spaces just because the construction is giving you those things. And it's then reasonable to ask whether this family of vector spaces become a vector bundle or not. And that will lead you to consider this C inverse. And the reason why I write C inverse here instead of just C is just because some convention about where the group acts. So that's not really an issue. Okay.
Sorry, your B, you're thinking about that as a universal family, or?
No, I just want it to be a family of vector spaces, and I want to ask whether it becomes a vector bundle or not. Right. It's not, but it's a twisted vector bundle.
But the question was, is it automatically a universal family of representations? Which is,
I don't actually work with, I don't really need to work, well, yeah, yes, sure. Although I never think about things that way. But yeah, sure. Although, of course, up to the fact that you pick a representative in every isomorphism class, which is, if you spend any time working on moduli theory, this is the wrong thing to do. But this has to be done in this particular setting. And okay, example of that C. Well, the first case is easy. There is no C, because for one thing, there's no place to support that C, because the space is zero-dimensional. The second example, there is some C. The C can be written in terms of the classifying data of the group extension, which I will not bother to do. The third one is not too bad, but it's basically for each component you attach an absolute of unity, basically. But, let's not worry about that. So now the conjecture. Okay. I'm gonna be as vague as I can be, because that's what they do in the physics paper. Okay, so here's the conjecture. Which I tend to call the duality conjecture. It says that the geometry of the drift y is equivalent to the geometry of the space y hat together twisted by this C. And there's got to be a lot of questions or objections about this statement, because it's just vague enough so that it either it's either true for a stupid reason or fails, dramatically. Right? Because first of all, what do I mean by geometry? And secondly, what do I mean by twist by C? Okay, so these are the two, at least for me, these are the two main issues when to be addressed when I was thinking about this stuff. Well, so the answer is that you get to pick what you mean by geometry. What the physicists were saying originally was that conformal field theory on Y should be equivalent to conformal field theory on Y hat twisted by C. So, and of course, we don't really have a good definition of conformal field theory in mathematics, not that I know of. So, so therefore, you get to choose whatever mathematical version of conformal field theory that you think are appropriate. That will be what I mean by geometry here. There is sort of geometric theory that you can define on Y and Y hat, and there is the theory in consideration has to have the property that you're allowed to twist by some Tuchel cycle. Okay. So there are a bunch of those things that you can consider. And for today, yes.
That C is a flag one too?
Oh yeah, it's locally constant. Yeah. yeah, don't worry. All the technical issues are not that you want in the generalization that you like are not there. Okay, so the one that I want to talk about for the rest of today is Roman-Witten theory. Namely, we can ask whether, well, we can in fact do this. Namely, we can ask whether the Roman-Witten theory of the J of y is equivalent to the Roman-Witten theory of y hat twisted by C or not. And as you have been hearing about it for the past 3 weeks or so, there is a Roman-Witten theory for y. And I'm not sure if the Roman-Witten theory for y hat twisted by C has been discussed, but this theory exists. This theory exists thanks to the work of Pan and Run, who's everywhere. And Xin. Oh no, we're in. So Roman-Witten theory is one geometry that you can consider in formulating this conjecture. And I should, at this point, explain what I meant by this being deviated from the mainstream Roman-Witten theory, because first of all, I'm changing the target space. Well, that's not too surprising, but I'm changing the target space to a disconnected space. As you can see, y hat is always disconnected because out G action has to fix the trivial representation. And it can take other non-trivial reducible representations to other ones, but it has to fix the trivial one.
Excuse me, how do you recover y from y hat?
Well, no, you don't. But but it's not exactly. I mean, there are many dualities that that don't go two ways these days, right? Physicists tend to call things duality even if they just go one way. So I'm taking that. I mean, I get that comment a lot, but I think it's reasonable still to call it duality. It's better. I mean, it's definitely better than the original terminology being used by the physicists. But anyway, all right. So
Well, you can try K theory. That should be easier.
yeah, but it's done, right?
You can try K theory.
That's done.
Oh, it's not. Okay.
I mean, didn't you hear Xiang's talk in your seminar? That's done.
Just give me a chance to answer what
I mean, I have only 15 minutes left, so I have to be selective. Yes. Yes. Right, so where was I? Yeah, so there's one thing that makes this different from the mainstream stuff is this space is disconnected and you usually don't do that. And the second thing is that you have this funny twisted by a two's cycle business that has to be incorporated in order to make the statement true, and that's not usual. And in terms of in view of a global mirror symmetry where you have to move around the stringy Kähler moduli space, in this particular conjecture, no, I don't have to move around the stringy Kähler moduli space. I do not have to sum over the invariance or whatever. So this in some sense is, you can argue that this is technologically less advanced, but there is some interesting feature going on here because this conjecture is by nature a non-commutative geometry conjecture. So I'll try to explain what I meant by that during the throughout the proof. Okay, so I should probably say what this is. To say that two Roman-Witten theories are equivalent, nowadays the sort of commonly accepted way to do that is to say that, okay, if you look at the generating functions, they're equal. I mean, maybe you need the quantization operators or quantized differential operators or whatever, but in this case, I just conjecture they are equal. After some linear change of variables. Okay, so they're just on the nodes equal, supposedly. Now the issue is you don't have to believe this conjecture, right? You don't have to. You're not supposed to believe whatever a physicist tells you. I mean, you have to. Yeah, I mean, you have to think about what they say. I mean, it's always interesting to think about what they say, but you don't have to believe on the nose what they say. Sorry, I don't mean to. I don't mean any disrespect. You know. All right. But there's some. I mean, at this generality, there's some issue to worry about. As you've been hearing over the past 3 weeks, the Gromov-Witten series. I mean, Gromov-Witten invariants are supposed to. What am I saying? There's some Gromov-Witten invariants are defined by saying, okay, you pick some cohomology classes, you throw it into some moduli space, and you integrate. Right. So if you want to declare that two generating functions are equal after some linear change of variable, you better have the same set of insertions to start with. Right. Otherwise, your change of variable wouldn't be a change of variable that much. So this is what I mean by the zeroth order approximation of this problem. Namely, you have to match the cohomology. You have to match the insertions. I should at some point explain to you what the insertions are on the dual side, but in order to make sense of a conjecture, you at least have to check that the cohomology of the inertia stack is equal to, at least additively, the cohomology of the inertia stack of y hat with coefficient in some local system. And this C came from the fact that you have your cocycle. You have your cocycle being in H2 with U1 value, and if you d-loop it once, you get H1 of the loop space. So that's d-loop or looping, I don't know. This is related to H1 of the loop space with U1 coefficient, and that's a line bundle on the inertia stack. But anyway, so maybe I should just say that. Loop space. Okay, so that's at least the very first question you should ask yourself. And of course, if you don't have any general approach, you look at this question in examples, and in examples, it all checks out. So therefore, that's some evidence to believe what physicist tells you. So fine. But then I'm not exactly sure what's been discussed in the past few weeks, but it is known that on these cohomology vector spaces, there are more structures. Right? There are funny gradings to be put on this, and there are there are interesting ring structure to be placed on this thing. And those things are all sort of classical limits of the full Gromov-Witten theory. So therefore, you have to, if you want to believe that there is an equivalence, there is an equality between a full Gromov-Witten potential, you must believe the following thing is true. You must believe there is an isomorphism between the turnaround orbifold cohomology ring on the gerb and the twisted orbifold cohomology ring on the dual. That's graded algebras. And this is the main theorem that we kind of worked out. I mean, of course, and like I said, if you don't know how to believe in such a statement, you check it by examples. And in examples, it all checks out, even at the level of graded vector spaces. But then you start thinking how I'm going to prove the thing in general. Because it wouldn't make much sense to say that conjecture if you don't have something like this.
What's the difference between orbifold cohomology and chain random cohomology?
This is, I mean, I say orbifold just because this was worked out by Run only instead without Chen. Right. And this, I mean, I have this U1 two-cycle twist in that side, and that's only worked out by Run as far as I remember. I mean, you decide the terminology. I mean, of course, it's the same thing, but you decide the terminology. Okay, so yeah, so that's the theorem. Okay, so now how do we sketch a proof? Okay, in 7 minutes. Okay, that's not going to work. Well, we'll see. So, I mean, the proof is really about understanding what this duality really means. So the first thing is to observe that, in fact, the J of Y and the dual pair can be put into equal footing and become isomorphic on the nodes after you think about them as non-commutative spaces. See, like I said, this deviates from mainstream Gromov-Witten theory because you rarely hear this word in a standard Gromov-Witten context. This is, by the way, in the sense of Kang, which makes it even reasonable to talk about it in France. Okay. All right. So just to give you an idea about what this is, I mean, why this is supposed to be the case. So just think about the case of BG. Okay. And the non-commutative geometry tells you that if you want to study a space, you should look at the algebra of functions. So you do that. That tells you should look at the group ring or group algebra. And there's something that's called Fourier transform nowadays, which tells you that this is equal to the direct sum of endomorphism algebra over a collection, over a set of representatives of irreducibles. Okay. So it makes it even more appropriate to talk about it here because this is, after all, the hometown of Joseph Fourier. But anyway. Now, this guy itself is highly non-commutative, of course, because this is just a direct sum of matrix algebras. Its center, of course, is going to be commutative. And well, basically an algebra is usually a Morita equivalent to its center. So therefore, if you take that, you take this algebra and take it, pass it to its center, then you get direct sum of copies of C, one for each irreducible representation, which is justifiably called the algebra of functions on G hat. Right? The space G hat is just a bunch of points. Functions on them are just one value at each point. So that's what's happening here. And if you look at the question, if you look at this question in the context of non-commutative geometry, it becomes apparent that why these two things are supposed to be related. It's just at some level you have to do a Morita equivalence, but Morita equivalents are considered as isomorphism in non-commutative setting anyway. So therefore, this at least suggests what's how you should think about things in general, because after all, a GGF is just a family of BG in some sense. So what you do is you look at the group you pick some you pick some groupoid representative and look at the groupoid algebra associated to that and build a Morita equivalence to get to the twisted group algebra for this guy. Okay, so that was not bad, right? So I should say let me just write this sort of informally. A groupoid algebra for Y is Morita equivalent to C twisted groupoid algebra of Y hat. Okay. That's what I really mean by the first step. They are the same as non-commutative space. And now the next step is the next step has to do with what the other thing is in the title, namely. So, well, 2 minutes. Okay, we'll do it. So remember, the ultimate goal is to get something cohomological. So you have to, now at this point you have algebra, so you have to do some standard construction to get cohomology, and the standard thing to do will be Hochschild cohomology, or periodic cyclic cohomology, or whatever you like. It turns out Hochschild cohomology works fairly well, but if you just take the Hochschild cohomology for this group algebra, you're going to get like polyvector fields. That's not quite, that's not quite bad. So here is what you're supposed to be doing. So Hsian-Hua in his thesis, he tells us how to construct a deformation quantization for groupoid algebras like this. So we construct that. So we take that. And just the way that the Morita equivalence is built, the after deformation quantization, you still have Morita equivalence. Okay, that's step 2. And because the two algebras are still Morita equivalent, if you now take the Hochschild cohomology, they're going to be isomorphic anyway again. But now the question is to compute this Hochschild cohomology, but that's actually done a bit earlier in joint work with Flan and Hassel. So with enough work, you can actually compute this Hochschild cohomology of deformation quantized algebras, and you get cohomology of the inertia stack with funny coefficients. So that's fairly close to what we want over there, at least additively. But of course, there is some issue about this coefficient coefficient here. The h bar is allowed to be inverted. But then the point is that we actually are working with a specific Morita equivalent, so we can write down the induced isomorphism between these two, and we see that there's no h bar in the formula, therefore, fine, drop it. So now the next step is the final step, of course. Now that we have we run some general machinery to give us additive isomorphism. And not just any additive isomorphism, there is a specific one coming from a natural construction. So, okay, let's take that one and see if we can prove that this one respects the ring structure and the grading. And for that, you just have to work. Right? You just have to, the goals are straightforward. There's no trick to do. You just have to compare the grading and compare the structure constants. Well, actually, there is some trick that allows us to compare the structure constants, but, well, I'm -1 minute left, so I think that will be it. Yeah. Thank you.
Are there questions or comments?
Yeah. Q variables are, I mean, Q variables keep track of second homology, which is the same on both sides.
Oh, so it's obvious at the moment.
Yeah, well, you suppose, I mean, that's where, well, in some cases, well,
If you run as a maybe disconnect.
no, it's, yeah, but, well, what am I trying to say? There is, I mean, the identification is, if it works out, it's going to be the following way. You're going to receive some rescaling at the Novikov variable given by the twisting cocycle C, depending on the degree of the variable, of course. But yeah, that's in any example that's been computed so far, that's what happens.
Another question is, can you enhance this to a isomorphism like direct pattern?
There is, you mean coherent sheaf?
Yeah,
There is an isomorphism. There is an equivalence of the abelian category of sheaves, so it's already there. It's even stronger. I mean, this is also a way to say that this duality is really something non-commutative geometric because there's a categorical identification between the sheaves. Yeah. I mean, that's why the paper was 70-something pages long. But